Okay, so this is problem 8.2b, and it's very similar to 8.2a, except for you have this little guy right there, and he's actually kind of annoying, but we're gonna get through it. Okay, so we're going upon the same base assumption that our equation looks like this. X to the n. Okay, and keep in mind it looks like this because we are centered at 0, so we don't have to worry about another term over there. Well, over, you know what I mean. Okay, take our first derivative. We're going to get 0 a sub n x to the n minus 1. Okay, and now to our second derivative. And we're actually going to play around with our second derivative a little bit and just show all the different ways you can display this. And we'll put that into play later into the problem. So a sub n minus 1, x to the n minus 2. So that's probably the way you would do it naturally. Do keep in mind you can evaluate this at 1 and 0. So if you evaluate this whole thing at 1 and 0, the first two terms are 0. So we can rewrite this as y prime in starting at 2, because we know that the first two terms are 0, and we don't really care about 0 terms. Okay, so that one probably made really good sense. There is one more way that we're going to write this, and hopefully it makes sense as well. So for those of you who don't remember, when you're dealing with an index and you want to mess with the index of a function, you can subtract from your index. So start your index at 0 here. When you subtract here, when you subtract here, you have to add them everywhere else. So you get a n plus 2, n plus 2, n plus 1, and then x to the n, because the 2's cancel out. So that's all the different ways that we're going to write our second derivative, and we'll see where that comes into play later. So we're just going to plug in our whatever you want. You can plug in any of these forms. I'm going to start with this. So we have our summation at n equals 2. A sub n minus 1, x n minus 2. Okay, and then distributing this x squared term, it goes in and becomes a sub n x n plus 2. And I forgot all the annotations on my summation. But that's okay. So n equals 0. So we're pretty far from anything matching the way we want it to, because our indexes don't add up and neither do our exponents. So we have a little bit of manipulation to do. So what I'm going to do is I'm going to subtract 2 from this index and get it into this format. So we're going to rewrite this as summation n equals 0, a n plus 2, n plus 2, n minus 1, and then x to the n. Okay, and for now, I'm just going to leave this second summation alone. N plus 2. Okay, so now we're going to evaluate this at 0 and 1, because we're trying to get, I know it sounds crazy because we just took it from n equals 2. We're trying to get it back to n equals 2, but in a way that will allow us to combine these exponents up here. So to get it back to n equals 2, we're going to evaluate this at 0 and 1. So when we evaluate this at 0 and 1, so 0 gives us, I don't know why I keep making that negative, positive. And that's just 2 zeros. 0 and 1. So when you evaluate this at 0, you're going to get 2a2. And when you evaluate it at 1, you're going to get 6a3, and then you still have a function of x in that. So keep that in mind. I'm going to go ahead and make my screen smaller so we can go from there. Maybe I'm going to make my screen smaller. There we go. It's really not. Okay. Okay, it's starting a whole new. Okay, you know what? I'm just going to take it out of tablet mode. And make this smaller. Okay, now we should have enough room, hopefully, to finish the problem. So we left off here. So we could get this index back to 2. So in doing that, we can rewrite our equation. N equals 2, 0, and it's going to look pretty much the same. So we have a n plus 2, a n plus 2, n plus 2, n minus 1, x to the n, and then we can't forget these terms, so we have to add them back in. So I'm actually going to do that over here, plus 2a2, and then plus 6a3 with that power of x. And we still have this second summation term, so we're going to go ahead and include that as well. And I know you might be thinking, we just got our indexes to match, and now this crazy lady is going around and changing them all up again, but I promise there is a method and we're almost to the end. N minus, x, that should be it. X to the n plus 2. Again, so sorry it's messy. Okay, so hopefully maybe now you are seeing what I'm about to do. So we have this at n equals 2, and we have this at n equals 0. So what I'm going to do is I'm going to re-index this again. So hopefully that makes sense. So I'm going to re-index this again to n equals 0. So that's going to give me, so we have n equals 0. And so when I subtracted the 2 here, I have to add it everywhere else. So I get a to the 4, well, a to the 4 plus n, and then n plus 4, n plus 3, and then x to the n plus 2. And there's that exponent we have been looking for. I don't actually think I have room to write the rest of it, so I'm just gonna, and it's still equal to 0. So that puts us a lot closer. We can finally combine our summations. So we have 2a2 plus 6a3 with 1x power, and then plus the summation of n beginning at 0 to infinity to our big an plus 4, n plus 4, n plus 3, plus a to the n. Okay, so hopefully this makes good sense, and we have x into the positive 2 that we were able to factor out. So being that the whole equation equals 0, we know that these, we know that these two terms have to add a 0, and this part here has to go to 0 too. So in saying that, I know you guys probably aren't used to having an x right there, but don't freak out about that. Don't worry about it, because for this this part to go to 0, a3 and a2 have to equal 0 at the same time. So the x doesn't really matter because we need the coefficients to be 0 for this to be true at all. So we're going to assume that a2 equals a3 equals 0. So hopefully that makes sense. And then also, like the prior ones, we're going to assume the ones we have not solved for equal just constants. So we have a naught and a sub 1 equaling a naught and a sub 1. Okay, so solving for this, we're going to solve for our a n plus 4. So we have a n plus 4 is going to equal our negative a to the n, and then over n plus 4, n plus 3. And that is our base equation that we're going to use to solve for the coefficients. Like I said, this is a little bit better because we have all the way up to a plus 3, and we're only needing to find the first 6 terms anyways. So it's a little bit easier in that regard. That's about the only regard that it's easier. But let me go ahead and make this smaller once again so we can begin to solve for the actual coefficients that will be ultimately in your answer. Okay. This is the last step of what we're doing. So we have a sub naught equals a sub naught. We have a sub 1 equals a sub 1. We have a sub 2 equals 0. We have a sub 3 equals 0 as well. So for the next terms, we're going to use this formula to get there. So we're looking for a sub 4. So what value of n is going to get us to a sub 4? So we have a sub n plus 4. So we're going to use n as 0 there. So for n equals 0, you get a sub 4, and then plugging into this equation, so we have negative a sub naught. For n equals 0, we have, so 0 plus 4, 4, and then 0 plus 3. So we have negative a sub naught over 12. Okay, so now we want a to the 5. So we're going to put n equals 1, gives us a to the 5. Okay, so when this equals 1, we have negative a 1. That's just a 1, not an 11, but You guys got it. So when n equals 1, we have 5 times 4, so we're going to have a negative 20. Well, negative 1 over 20, but you guys got the gist. And then for n equals 2, I think we don't technically need this, but I'm just going to go ahead and do it for safe measures. Gives us a sub 6. So for when n equals 2, we already know that when we plug this in, we're going to get a negative 0 on top and some gobbledygook down here that we don't care about because 0 in the numerator means it goes to 0 there. So those are your coefficients for this problem, and hopefully it made good sense. Let me know if you have any questions at all. So, bye.